Have you ever just stopped and wondered, how does the internet actually work? I mean, how does it not just completely collapse on itself every single day? Well, today we're going to pull back the curtain on the secret rules that keep it all running. We're talking flow control, congestion control, and the protocol that manages it all, TCP. Let's get right into it.
I mean, seriously, think about it for a second. You're streaming a 4K movie, your roommate is gaming online, millions of other people are on video calls, all at the same time. How does the whole thing not just grind to a halt? Well, it's all because of some incredibly smart traffic management happening behind the scenes, and that's exactly what we're going to break down.
Okay, so if you're studying for your DCN exam, you've definitely come across these two terms, flow control and congestion control. And let's be honest, they sound pretty much the same, right? It's a classic point of confusion. But here's the thing, they solve totally different problems. Stick with me for the next few minutes, and I promise this is going to be crystal clear.
All right, first things first, let's cover the absolute basic building block of the internet, the packet. What is it? Well, when you send an email or watch a video, that huge file isn't sent as one giant chunk. Instead, it gets chopped up into thousands of tiny little pieces. Each one of those pieces is called a packet. The best way to think about it is that the internet is a giant postal service, and your data is being sent as a whole bunch of tiny little letters.
So let's tackle our first big topic. Section 1, flow control. The name kind of gives you a big hint, right? The whole idea here is really simple. Don't flood the receiver. We need to make sure we don't send data so fast that the computer on the other end just can't keep up.
So here's the exact problem it's trying to solve. Imagine you have a brand new, blazing fast computer, and you're sending a huge file to your friend who's using an older, slower laptop. If you just blast that data at your maximum speed, their poor laptop is going to get totally overwhelmed. It's like trying to get them to drink from a fire hose. It can't process the information that quickly, so packets will just get dropped and lost.
And that's exactly where flow control comes into play. Think of it as a direct, private conversation happening between just the sender and the receiver. It's a one-on-one chat. The receiver can literally send a message back that says, "Whoa, hey, slow down a bit, I'm falling behind." Or, "Okay, I'm all caught up, feel free to send more." The entire goal here is to protect the receiver from getting swamped.
So how does this actually work? Well, the simplest method is called stop and wait, and it's, well, exactly what it sounds like. The sender sends one packet, and then it stops. It literally waits for an "okay, I got it" message to come back. We call that message an ACK for acknowledgement. Once it gets that ACK, it sends the next packet. It's very safe, but as you can imagine, it's incredibly slow. That's why there's a much smarter method called the sliding window. In this case, both sides agree on a window size. Let's say it's 10 packets. Now the sender can send all 10 of those packets at once without waiting for an ACK for each one. It's way more efficient.
Okay, great. So we've made sure the receiver is safe. Problem solved, right? Well, not quite. What about the network itself? What about all the roads and highways in between? This brings us to a much bigger problem. Congestion control.
You see, the problem is bigger than just your computer talking to your friend's computer. It's about the entire internet highway system. You've got millions, maybe even billions, of these conversations all happening at the exact same time, all trying to use the same shared roads, the same routers, the same cables, and if everyone tries to go full speed at once, you get total gridlock, a massive network-wide traffic jam for everybody.
And this isn't just some theoretical problem. This actually happened. Back in 1986, the early internet suffered something called a congestion collapse. The whole thing basically broke. Data speeds dropped by a factor of 1,000. It was a total disaster. So a couple years later, a brilliant engineer named Van Jacobson came up with the algorithms for TCP that essentially saved the internet. And we're still using his core ideas today.
So congestion control is not that private conversation we talked about earlier. Its job is to protect the entire shared network. If flow control is a private phone call, congestion control is like a public traffic report broadcast to everyone on the highway. The sender doesn't wait for the receiver to say slow down. Instead, it's always looking for clues that the network itself is getting jammed up, like lost packets. And when it sees those signs, it slows itself down to be a good citizen of the internet.
And this slide right here, this is exam alert territory. This is pure gold. If you get a question asking for the difference between the two, this is your answer. Burn this into your brain. Flow control is point-to-point, a private call to protect the receiver. Congestion control is about the entire network, a public traffic report to prevent total collapse. You understand this, you are halfway to an A.
So we've got these two huge problems, flooding the receiver and jamming up the whole network. How does the internet actually solve them both? Well, it's time to meet the hero of our story, TCP.
TCP. It stands for Transmission Control Protocol, and it is the absolute workhorse of the internet. Its number one promise, its main job, is reliability. When you send a file with TCP, it's making a promise that every single one of your packets will arrive safely and in the correct order. And how does it pull off this magic trick? By being smart enough to handle both jobs. It manages flow control and congestion control all at the same time.
So how does it manage all this so well? Well, TCP has a very clever set of rules for how to behave on the internet highway. Let's take a look at its strategy for controlling congestion.
Okay, I know what you're thinking when you see this. A graph. Looks complicated. But trust me, it's not. This graph tells a very simple story about how a TCP sender decides how fast to send data. All you need to know is, the higher the line goes, the faster it's sending. And the line moving to the right is just time passing by.
So let's break this story down into 4 simple steps. First, TCP starts with slow start. It's polite. It begins by sending just a little data, but then it quickly ramps up, doubling its speed over and over to find out how fast the network can go. Once it gets close to that limit, it switches to step 2, congestion avoidance. Now it gets more careful. It increases its speed slowly, just a little bit at a time. Then, step 3, a packet gets lost. To TCP, a lost packet is a giant red flag that screams, "Traffic jam ahead." So what does it do? Step 4, it reacts fast. It slams on the brakes and dramatically cuts its sending speed way back to give the network a chance to breathe.
Now look at the graph again. You can see the story perfectly, can't you? See that really steep curve at the very beginning? That's the fast exponential growth of slow start. Then notice how it changes to that gentler, steady upward slope. That's the cautious one step at a time increase. And then, bam, that huge sharp drop. That's TCP hitting the brakes when it detected a problem. It's this constant dance of pushing the limits and then backing off that keeps the entire internet working for all of us.
All right, let's bring it all home. We're going to do a super fast revision to lock in these concepts for your exam.
Here's the absolute bottom line. 1. Flow control is the one-on-one conversation to protect the receiver. 2. Congestion control is for the entire network, to prevent a system-wide traffic jam. 3. TCP is the smart protocol that does both to give us reliable service. And 4. TCP's method is to grow fast, then grow slow, and slam on the brakes when there's trouble.
Okay, seriously, if you only remember 2 things for your test, make it these 2. First, the clear, undeniable difference between flow control and congestion control. One protects the receiver, the other protects the network. And second, the basic idea of TCP's strategy. Start fast, then go slow, and back off when there's a problem. Got it? Good.
And just to help you prepare, here are 5 questions you might actually see on your exam. Try pausing and answering them in your head right now. If you can do it, you've totally got this. If you get stuck, no big deal. Just rewind a bit. All the answers are right here.
And that's pretty much it. So the next time you're binge watching a show or downloading a big file without a single glitch, just take a second to appreciate that complex, invisible ballet that's happening behind the scenes, all thanks to TCP. It's pretty amazing. All right, good luck with your exams.